Hi everyone! In today's video we are going to talk more about exponentials and logarithms, and today we're going to be evaluating them. So we are first going to talk about how to rewrite logarithms in exponential form, and then we're going to be evaluating logarithms by exponentiating them, by using logarithmic properties, by graphing, by using the change of base formula. And then we're also going to be expanding and condensing logarithms today. So first, what we need to talk about is logarithms and their bases. So when you see a logarithm, a lot of times, though not always, it's going to have a number down here. That b value is the base. And that number is going to tell us what number system we're working in, essentially, what base of the number system. So are we working on a 10-digit system, that's log base 10, a 2-digit system, log base 2, those sorts of things. So the nice thing about logarithms is that they are related to exponentials. As we talked about last time, they're inverse functions of one another. So we can take a logarithm if we know log base b of y, remember that y is in parentheses, is equal to some number x. That is the same thing as b, that base, raised to the x power is equal to the y value. So we can flip back and forth between these two notation formats as it's convenient for us depending on what we're trying to do. So first, let's just work on going back and forth between those. I want you to notice that we're going to start with the base. We're going to go up and grab the exponent, and then we're going to go to the input value of the logarithm. So it makes this like swoopy motion that I like to think of. So if we're going to rewrite this first, log base 2 of 8 is equal to 3. We're going to start with the 2. We're going to raise it to the third power and say that it's equal to that input value. So 2 to the third power, and what is 2 to the third power? You know how to do that math. It's 8. So that's a true statement. Those things are equivalent to one another. Log base 2 of 8 is 3. Let's look at number 2. Log base 4. We're going to raise it to the 0 power, and that equals 1. 4 raised to the 0 power, well, anything raised to the 0 power is 1. Let's look at this next one. The base of 7. 7 raised to the first power. 7 raised to the first power is 7. And one last one, let's take this fraction, 1/4 raised to the negative 1 power is 4. So that's 1/4 raised to the negative 1 power is equal to 4. And if we think about that, the negative 1 exponent flips the fraction bar, right? It takes the bottom to the top and the top to the bottom for whatever the base is. So it flips over to be 4 over 1 to the first power, which is just 4. So that all checks out. When you do this conversion, if you're just working with simple numbers, you should always get something that's an equivalent or true statement. So that's always something you can do to check to make sure you did the rewriting correctly. Okay, so now let's look at evaluating. When we need to evaluate a logarithm like log base 4 of 64, we're going to say, okay, let's say that's equal to some variable, y. And then we're going to use that rewriting. 4 to the y power is equal to 64. So if I rewrite that, 4 to the y power is equal to 64. And then I need to think about what power does that need to be? 4 raised to the third power is 64. So that means that y has to equal to 3 because it makes that exponential statement true. So log base 4 of 64 is 3. Let's do another one. Base 5, we're setting it equal to y, so that y will be our exponent, is equal to 0.2. Now I'm going to write 0.2 in this one as a fraction because that's going to help us to see things more easily. I'm going to write that as 1/5. So you'll notice here that the base 5, it has to go down to the bottom, down to the denominator, so that means this y value has to be negative. And it's going to be a 1 because the 5 doesn't change at all, it just moves. So then log base 5 of 0.2 is equal to negative 1 because 5 to the negative 1 power is 1 over 5. Okay, let's look at one more, or two more. 36 to the y power, remember we're setting it equal to y, is equal to 6. So we need to take 36, we need to raise it to some power and get 6. Now what I immediately think of is the square root of 36 is 6, right? So if we write that square root as an exponent instead of as a fraction bar, so that's 1/2, that gives us an exponent. The y value is 1/2, and so the log of 36 base 6 is equal to 1/2. All right, last one. Our base is 1/5. We're going to raise it to the y power, and we need to get 125. So I noticed that I went from a fraction to not having a fraction, so that means that I'm going to have a negative number. And then to get from 5, once it flips up to the top to 125, that's to the third power. So it's going to be 1/5 raised to the negative 3 power, and that's our answer, is equal to 125. Because when I flip it, that gives me 5 to the third, and 5 to the third is 125. So when you're evaluating logarithms using this exponentiating format, or changing the logarithm to an exponential, we are really just kind of playing this game of finding the missing number, if you will, using your math facts. Okay, so let's talk a little bit briefly about some logarithms. The most common logarithm that you're going to see is log base 10. And because this is such a common base in our system, we're just going to write this as the logarithm of x, or log x. We're not going to write the 10 if it's base 10. When we have other bases, that's when you're going to see that number. In the calculator, whenever you hit the log button, you're doing log base 10. It's just an abbreviation of that really common format. So in this problem, log of 100, because there's no number written here as the base, we're going to assume that's a 10. So if we wanted to evaluate log of 100, that's log base 10 of 100, we can set it equal to y, just like we were doing before. The base 10 raised to the y power is equal to 100, and then we need to ask ourselves, what power does that need to be? 10 to the what power is equal to 100? That is going to have to be a 2. So log base 10 of 100 is 2. Okay, the next type of special logarithm that we're going to have is called a natural logarithm. And the base number for this special logarithm is base e. E is kind of like pi. It's a special number that comes up a lot in different mathematical endeavors. So it's approximately equal over here to, generally we round this to 2.72 if we want to round it the same way we do 3.14 for pi. It's this number that this expression 1 plus 1 over x raised to the x approximates, or it gets really close to as you look at the right hand side of that rational expression. So we're not going to go a lot into this number e. The name for it is the Euler number. So to pronounce that, it's Euler. So oil and then Euler. Let me write that a little bit more neatly. That's kind of messy, isn't it? So Euler, the Euler number E. So the Euler number E is really nice because it is going to be the inverse of a natural logarithm. So when we write log base e of x, we're actually not going to write that. Instead, we're going to write the natural log of x. All natural log means is that we're working with base e, the same way a moment ago we were working with log base 10. So if we see natural log of 5 and we want to approximate that, we can write that as log base e of 5. And then we can solve that in a similar manner, though this has a little bit of oddity in it. That's e to the y power is equal to 5, and we're looking for what that y value is. Now, if you are able to use a calculator, then going into Desmos can help you with this. So if we wanted to, let me pull it up over here. If we wanted to do log base e of 5, we could go to function over to miscellaneous and choose our log base. We could also choose natural log in this calculator, but for the sake of showing you, I'm going to put it in here. For my log base, then I'm going to, I need my keyboard to put an E in there. Oops. Let's see. All right, it doesn't look like my keyboard is connecting well. I have to use my mouse, and I don't think I have an option. Let's see real quick. Do we have the Euler number anywhere in Desmos? Unfortunately, it looks like they are not that fancy. So instead of doing that, sorry, I am, because my keyboard's not cooperating, just going to use the natural log button. If I put in the natural log of, and then I can hit 5 here, it gives me my 1.609, let's round it there, approximation. You would be doing ones like this with the calculator, not by hand, of course, because I wouldn't expect you to know e to the sum powers equal to 5. In this case, though, when we did it in the calculator, that is approximately 1.60945. So that natural log of 5 is approximately equal to that value. So natural logs, we're going to go back and forth between e and natural log when we're solving sometimes, because it's going to make our lives easier, because they undo one another in a similar way that squares and square roots undo one another. Okay, so with that, let's get into some actual using logarithms. Just like when we did exponents, we have rules or properties that are going to be relevant to logarithms, and these are going to help us simplify problems. So the first is the product property. So inside of some logarithm, if you have a number that's can be broken down into 2 factors, so like 24, for example, 24 is 4 times 6. So because I can break that down into factors, that composite number, I can also break the logarithm into 2 logarithms. So this is log base 5, and log base 5 of 24 is equal to log base 5 of 4, one of the factors, plus log base 5 of the other factor, 6. And sometimes it's going to be really helpful to be able to expand it in this way, or to break it down into pieces with other factors as the numbers we're working with. Similar to with our exponent rules, if you have division this time, so a number that you could split into a divisor, then we're going to be subtracting instead of adding. Notice the multiplication got added, the division gets subtracted. The same way, or in a similar way to what it worked with the exponent rules. So 18 is the same thing as 36 over 2, or 36 divided by 2. So that means if I needed to, I could rewrite log base 4 of 36 minus, because that's division, log base 4 of 2. If inside of a logarithm you have a power, then that power can be brought out to the front with multiplication holding it to the log. So when I see log of 16, I might notice that 16 is 4 squared. And so because log base 10, in this case, of 4 squared has an exponent, it might be useful when I'm simplifying some problems to take that exponent of 2 and say 2 times the log of 4. The other 2 properties are pretty related to one another. It says that if you know 2 numbers are equal to another, you can put both of those numbers into a log of the same base, and those statements will also be equal. So if you know 3x is equal to 6, then you know log base, I don't know, whatever you want, 7 of 3x is going to be equal to log also base 7 of 6. So we can incorporate logarithms into both sides with whatever bases we need them to be for our expression to work out. And likewise, if you have a log that has the same base that's equal to another log of the same base, then the inputs of those 2 have to equal one another as well. So in this case, x is equal to 7 because those are both logarithm base 2's. Okay, so let's do some actual applying of these properties to simplify. So in this problem, we are given 2 important pieces of information. We're told approximately what log base 4 of 3 and log base 4 of 7 are. So what we want to do is we want to see if we can use those properties to break up the problem so that we can then convert to these approximations that were given, not using a calculator or anything like that. So this first one, I immediately see it has a 3 and a 7 in it, and this one it's division. So I'm going to use that quotient property that we just talked about, the second rule, to say log base 4 of the top 3 minus, instead of dividing, log base 4 of 7. And the reason that I like that is because log base 4 of 3, in the directions, I was told that's equal to approximately 0.792. I was also told log base 4 of 7 was equal to approximately 1.404. So I can substitute in those approximations now that were given, and I can do that subtraction. I get negative 0.612 there, and then I've done that that simplification using those logarithmic properties. With one like number 10, remember I want to use a 3 and a 7 because that's what I've been given in my directions as the logarithms that I know the values for. So I immediately think of log base 4 of 3 times 7. Because when I have two numbers multiplied together, I can break those up into log base 4 of the first one plus log base 4 of the second one. And then again, I can use that substitution. Log base 4 of 3 is at 0.792, and log base 4 of 7 is that 1.404. And then I can do that basic addition to get 2.196. And that is my approximate value for log base 4 of 21. And I guess technically here, if we want to get real picky, we should say that this is an approximation here, and because we did that substitution there, that's an approximation as well. So we'll be picky today. Okay, so the other piece with the properties of logarithms is going to be expanding and condensing. So we can use these properties to break up logarithms to be an expanded version, or if there's a bunch of stuff going on, we can condense it all into one logarithm as well. So in this first one, log base 5 of x times y squared, we have multiplication and we also have an exponent there. We're going to split up the multiplication first because the y is being squared but the x is not. So we can't just use that power rule to pull it out because it doesn't involve the x. So the multiplication rule said we can do log base 5 of x plus log base 5 of y squared, that second base there. Now this log base 5 of x is done at this point. There's nothing else that I can expand because it's just an x inside. But the log base 5 of y squared has this square. So we're going to use that property now to pull that 2 times log base 5 of y out front. And now this one just has a y. There isn't any other operation happening inside of it. So that means I've expanded this one as far as I can. We can do the opposite of that and combine as well. We have log base 4 of 7 minus log base 4 of 10. So if we have two logarithms with the same bases that are being subtracted, that means that's the quotient property. So we can say log base 4, and then our division is going to be the first number 7 divided by the bottom number 10. And that combines that all together into one logarithm base 4, which might help us if we were solving a problem just to make the problem a little bit more simple to deal with. The next thing, the third big thing that we need to talk about is if we want to evaluate by graphing. So we've talked several times this year about taking an equation or a function and making it a system of equations. And that's essentially what we're going to do. We are going to set it equal to x because we're trying to solve for x most of the time, right? And then we're going to convert it to exponential form. So we're going to do that piece that we were talking about at the beginning. We're going to take our base, raise it to the power, and then say that's equal to. So we've got 3 to the x power is equal to 50. Now we have an equation. That means we can graph a system of equations. We're going to take the left-hand side and plug it into the y equals, and the right-hand side and plug it into the y equals as well. Now, roughly speaking, it's going to give us a picture that looks like this, where this is y is equal to 50, and this line, y is equal to 3x 3 to the x power, and this line is y is equal to 50. Whatever this intersection point is, that ordered pair, something 50, that is what x is equal to. And so that's what log base 3 of 50 is equal to. So I'm going to hop over to Desmos real quick and get this graph so that we can see our evaluation without having to do too terrible much work. Okay, so we've got for the first one, y is equal to 3 raised to the x power. That gave me my exponential function, and then y is equal to 50. Okay, so I've graphed my 2. It hasn't shown up here, but 50 is a big number. I need to zoom out. So before I do that, I'm going to switch into a mode so it's a little easier to see everything like I normally do. Okay, and then after I've done that, you can either drag up or you can zoom out. Now I'm going to do a little bit of both because I don't want to zoom out too terribly far. But once I get far enough out, I can see my purple and my green lines now. And if I click, then I'm going to be able to click on that point and I can see that x is 3.561. That means then that this logarithm is equal to that value, approximately. So because the x value here is 3.561, log base 3 of 50, my problem, if I wanted to evaluate that using a system, I could get to that approximation that it's 3.561 by using that system of equations. Okay, the last thing that we need to do is looking at the change of base formula, which we're going to use a little bit today, and we're going to use it more next time when we're solving. So the basic idea is that if you have a logarithm or 2 logarithms that are the same base, you can change, or let me start again. If you have a logarithm with a base, you can change it to be 2 logarithms with different but the same bases. So what that's going to mean is we can take something like a log with some base that's not a 10 because we like the 10s, it's the common one, and we can change it to be log base 10. So let's look at an example of that. If I have log base 3 of 18, the change of base formula says that I can change that base. I can make it not a 3 base anymore. I can make it log base 10 if I say the logarithm of my input, 18, divided by the log base 10 of my original base, 3. So these are both log base 10s now. Notice I didn't write the little 10s because those are implied, but these two things are equivalent to one another. If you need an exact answer evaluating a logarithm with the change of base formula, this is it. You can't get any more specific than that. Now in a calculator, if you put in log of 18 divided by log of 3, it's going to give you an approximation. I'm not going to go over to Desmos and do this. I'm just going to ask you to trust me that it's 2.631. That is our approximate answer. So we can get the exact answer with change of base formula, or we can get the approximate answer by plugging that change of base exact answer in. The same thing is true with log base 12 of 400. If I use the change of base formula to make these both, again, log base 10, I can say the log of 400 divided by the log of 12 is equal. Notice that again, it's log base 10. That's my exact answer. If I were to plug this into Desmos, I would get as an approximate answer 2.411. Okay, the last thing that I want to show you is that we can also use the change of base formula with a calculator to help us with graphing sums. So if I have log base 3 of this quantity x plus 2, the change of base formula says that's equal to log base 10 of the input, x plus 2, divided by log base 10 of the original base 3. This is something that is going to be a little bit easier to graph, and in future years you're going to get more into that. For our purposes right now, we're just going to graph in Desmos real quick so we can get a sketch and we can do some practice with characteristics of the functions. So I'm going to hop back over to Desmos one more time, clear out these other things that I had, and then let's put in y is equal to, I'm going to go ahead and hit division so I get my fraction bar, Up top, I'm going to put in the log base 10, and that was of x plus 2. And then down in my denominator, I'm going to put the log base 10 of 3. So then, let's see, my screen is still kind of wonky from that last problem I did, so I'm going to zoom out. Oh, there it is. And then I'm going to zoom back in closer to my origin so we can see what's going on. All right, I'm also going to change my color because I think the black is a little bit harder to see with the grid also being black. Okay, so I have my logarithmic function graphed here now. I'm going to do what I did last time. I'm going to hit the wheel and then the table so that I can get some ordered pairs. We have that it's undefined at -2, which makes sense because that is where our asymptote is going to be. Remember, logarithms always have vertical asymptotes. And then I've got a couple of nice ordered pairs, -1, 0 and 1, 1 that I can graph. So let's go ahead over and get our nice but rough sketch over here using that. Our vertical asymptote was at -2. We had -1, 0, and then 1, 1, I believe. Yeah, okay, and then if we went out a little further, over at 7, it was up at 2 as well. Okay, so that'll give me just a slightly nicer picture. You can look at Desmos and get that information as well, of course. So let's talk characteristics to review a little from last class. The domain on the far left, it gets stuck at the asymptote at 2, but it goes all the way to the right. The range is going to be all real numbers because it goes down infinitely and it goes up infinitely. The asymptote, we are going through the x-axis at -2, so that means that's x is equal to -2. The x-intercept was at that ordered pair -1, 0. The y-intercept is going to be a fraction, right? It doesn't hit at a nice place. So I'm actually going to go back to Desmos one more time. I know I said I wasn't going to, but I need to get that x-intercept, because remember, the x-intercept will always be something you can click and get. 0.631 is my answer for that. So I'm going to write down that ordered pair. What did I just say? 631. Okay, so that gives me my values, my key characteristics for that graph. So we can use the change of base formula to make something that in the future years when you're doing more work with logarithms will be easier to graph when you have that. For our purposes this year, we will be using the calculator for logarithms, though to help you out, I care more that you're able to answer key characteristic questions like finding the asymptotes and those sorts of things. Okay, so in this video, we rewrote logarithms in exponential form, and then we evaluated logarithms lots of different ways. We exponentiated them, meaning we turned them into exponents to evaluate them. We applied those properties. We used the change of base formula, we graphed a system of equations, and then we also did a little with expanding and condensing, which we're going to be applying in your next lesson. So go ahead and try the Now You Try problems so that we can see how much you understand.